Welcome back to the School Science Shed. This is episode 7 in a series of videos that are designed to help you with your revision for GCSE Physics if you are studying in England. If you're not in England, the information that I'm covering is still correct physics, and I hope it will be useful to you. But you do need to check your curriculum to make sure that it's relevant to the things that you need to know. And even if you are in England, please don't rely on this series of videos as your only means of revision. Please check your syllabus to make sure that you've covered everything that you need to cover. In this episode, I'm going to talk about the important science ideas of current, potential difference, and resistance. So let's make a start. If you watched the last video, you would have seen that you already knew quite a few circuit symbols, but there are some extra ones that you need to know for GCSE. So on this slide, all of them except one you would have already seen before you even started your GCSE studies, but there's an extra one here, which is the fuse. And in a subsequent video, we will talk about what the fuse actually does. On this slide, there's a lot of new components that you need to know the symbols for. We've got a thermistor here, diode, LED, LDR, resistor you already know, and then variable resistor. In another video, I'm going to talk about these four. You already know what a resistor is from the last video. I will explain about a variable resistor though. So a variable resistor basically does what its name suggests. It gives you a resistance that you can change. A resistor is a component with a particular resistance that is a deliberate, it's deliberately difficult for current to flow through that component, and it has a particular resistance. With a variable resistor, you can actually change its resistance. You can make it have more resistance, or you can make it have less resistance. Again, if you watch the last video, you'll know that the current is a flow of charge. But we can actually write that as an equation. We can actually express the idea that if a current is flowing, charge is moving. And the way we do that is with this equation here. So the charge that has passed a point in the circuit, and the unit for charge is the coulomb, is equal to the current in amps times the time in seconds. And it's worth just talking about the abbreviations, the symbols that we're using here for the different parts of the equation. So in electricity, we've got a problem because we can't use the word C as an abbreviation because we've got current, which starts with C. We've also got charge that starts with C. So we need to have something different. So what physicists have done is they've chosen Q for charge, and the reason they've done that, I'm not sure about this, but this is why they've done it, because the unit is the coulomb. Coulomb, do you see where that's coming from? So Q is charge, and then I is current. Now, I have been learning and teaching physics for a very long time, and nobody has come up for me with a satisfactory explanation of why we use I for current. But it is the letter we use, capital I for current. I know why we don't use C, because that would be confusing with charge, but I simply can't tell you why we use I, but that's what we do. And you just need to learn it. And to be honest, you will soon get really used to the idea. Every time I'm teaching it, I have to remind myself that I isn't an obvious letter to use. And I have to take the trouble to make sure that people know I is current. And then time. And can I just point out, the time has to be in seconds. Now, we've got a lot of different ways of measuring time. Seconds, minutes, hours, years, days, and so on. Make sure, if you're doing the calculation, you're using a time in seconds. And the other thing we explained in the video last time was that most of the time, current, which is moving charge, is electrons that are moving. Remember, electrons have got a negative charge and they're normally in an atom. But if you've studied GCSE chemistry, you'll know that a metal has this structure. it's made of ions, metal atoms that have lost electrons, and because they've lost electrons, they've got a positive charge. What's happened to those electrons? Well, they're moving around in between the positive ions. And that's why metals are conductors, because these electrons, which are called free or delocalized electrons, are free to move. And because they're free to move, they can all move. And when they're moving, that is a current. That's why metals are conductors. Non-metals are not made of positive ions and free electrons, and therefore there aren't charges to move, and therefore non-metals tend to be insulators. And almost always, if a current is flowing, it's flowing because there are electrons moving. Almost always. Not absolutely always. So again, if you're studying chemistry, you will have learned that ionic substances are conductors if they're dissolved in water or if they're molten, if they're melted. And this diagram shows why. This is a diagram showing an ionic substance dissolved in water. So we've got water molecules, we've got positive ions, and we've got negative ions. And what you can see is all the positive ions are moving this way, all the negative ions are moving that way, and therefore this solution is conducting electricity. And that's why ionic substances are conductors, because the charged ions are free to move. And that's just showing you that although a current is almost always electrons moving, it's not absolutely always. It doesn't have to be electrons. Now, this video here is from a simulation that I've showed you before. This is PhET's circuit construction kit. It's a really good simulation, and if you want to, I thoroughly recommend for revising for electricity that you take a look at PhET and you have a go at setting up some circuits of your own and taking a look to see how those circuits work. It's really helpful in demonstrating your understanding. Now, there's a couple of points here about this. The first one is it's showing what I mean by a current is a flow of electrons, because that's what the electrons are doing. They're moving. It's also showing you how a switch works. Let's take another look at that. So, current flowing. At the moment the switch is closed, but if we open the switch, it creates a break in the circuit and therefore the current stops. So that's current. Current is a flow of charge. It's almost always electrons that are flowing, but it might be positive and negative ions of an ionic substance that's been dissolved in water or heated up and melted. What about potential difference? Well, another thing that you'll remember from the last video is that charge, when it flows around a circuit, transfers energy. And that especially happens when the charge is passing through a component. So when charge passes through, let's say, a lamp, it transfers energy into thermal energy and light. And the potential difference across that component tells us the amount of energy transferred for each coulomb of charge that passes through the component. That's what potential difference is. And I hope this picture demonstrates what's going on. So here we've got a power supply with 8 cells in it. So it's a 12 volt power supply. Therefore, it is providing a potential difference of 12 volts across this light bulb, and you can see the light bulb is really bright, and that's because for each coulomb that passes through this light bulb, it's transferring 12 joules. Very bright. If we take some of the lamps out and make a 6 volt power supply, look, the bulb is much less bright. One of the reasons the bulb is less bright is because for each coulomb of charge that passes through this bulb, for each coulomb that passes through that bulb, it's only transferring 6 joules into thermal energy and light. And that's one of the reasons why it's less bright. So that's what potential difference is. Sometimes people call potential difference voltage. That's not really the correct term, and I think it would be a good idea if you stuck to potential difference. But at GCSE you can get away with calling it voltage. But let's be honest, voltage is really baby talk. Calling potential difference voltage is the same, I think, as calling a train a choo-choo or a dog a bow-wow. Everybody knows what you mean, but it doesn't sound very grown up. So let's go for potential difference instead of calling it current. Definitely don't call it current. Let's call it potential difference instead of calling it voltage. Another way of thinking about potential difference is to think of it as driving the current through the component. So if we go back to this slide here, the 12 volts of potential difference across the bulb is, you can think of it as pushing the charge through that component. And the reason that works is there is a connection, isn't there, between giving something a push and transferring energy. If you want to transfer some energy to a toy car, you give it a push. So there is this connection. So you can think of potential difference as driving the current through the component. And the definition that we've just seen of potential difference leads us to this equation, which is that the energy transferred when charge passes through a component is equal to the charge in coulombs times the potential difference in volts. And that equation comes from what potential difference actually is. There is a triangle that goes with the equation, and if you want to know how to use that triangle, then take a look at the video episode 3b that I did about energy calculations, because that explains how to use a triangle like this. So if we've talked about current and potential difference, what about measuring those things? Well, in order to measure current, we use an ammeter, and the unit for current, as we mentioned before, is the amp, and we connect ammeters in series with the component we're investigating. So let's imagine we want to find the current through this lamp here. We connect an ammeter in series with that lamp. And actually in this circuit, it might not be true in all circuits, but certainly in this circuit, it doesn't actually matter where we put the ammeter, because the current is going to be the same all the way around this circuit. So ammeters connected in series to measure current. And we talk about the current going through the bulb. And you can see, can't you, if the current goes through the ammeter, it's then going to go through the bulb. So by measuring the current through the ammeter, we also know the current through the bulb. Potential difference you measure with a voltmeter. And the unit that you use is the volt, which is why we've got that baby talk voltage. And if you're measuring potential difference, you connect the voltmeter in parallel with the component that you're investigating. So in a circuit, it will look like this. And one way of remembering the right way round, remembering that ammeters are connected in series and voltmeters are connected in parallel, is to use the correct terminology, to always talk about current passing through a substance and to always talk about potential difference being across a component. So current through a component, potential difference across a component. So I said we talk about current, potential difference and resistance. Let's take a look at resistance. What the resistance of a component tells us is how difficult it is for current to pass through. More resistance means it's more difficult and will mean that the current will be less. So the current through a component depends on the potential difference across it, because we can think of that as pushing the current through the component, and it also depends on the resistance of the component. More resistance, less current; more potential difference, more current. And you can't measure resistance directly. You can measure potential difference directly with a voltmeter, you can measure current directly with an ammeter, but to find resistance you need to know the potential difference and the current. And if you know the potential difference and the current, you can then work out the resistance. And you use this equation to calculate resistance. It's potential difference divided by current. And the unit for resistance is the ohm. That's named after Georg Ohm, who was one of the first physicists to do measurements about potential difference and current. And then what physicists have done to think of a symbol for that is there happens to be a Greek letter omega, ancient Greek letter omega, the capital of which looks like this. So that's an uppercase ancient Greek omega. And you can see why they've done it. Ohm and omega are very similar, so it makes sense to choose that as the symbol for the unit of resistance. So resistance is equal to potential difference divided by current. And if you wanted to measure the resistance of a component, like this lamp in the circuit, what you do is you connect an ammeter in series with the lamp to measure the current through it, and you connect a voltmeter in parallel with the lamp to measure the potential difference across it, and then you do the sum resistance equals potential difference divided by current. There's a triangle which goes with this equation as well, and as I said on a previous slide, if you want to know how to use a triangle like that, take a look at episode 3b. And just finally, if we're talking about resistance, just to make it clear that there's a component called a resistor. It's designed to have a particular resistance and to be difficult for current to pass through. Here is the photo of some resistance. This colour code here actually tells you what the resistance in ohms of each of those resistors is. And if you Google resistor colour code, you can actually find out what the resistance of each of those resistors is. You do not need to know that for GCSE Physics. You do need to know the symbol for a resistor, which is this symbol here, this narrow rectangle in the circuit. So that takes us to the end of our video about resistance, potential difference and current. I hope it's been useful to you, and if it has, please give it a like. If you've got any questions, please put those in the comments. I've very much enjoyed explaining these ideas to you, and I'm looking forward to the next video. But until then, good luck with your revision.